In the previous section, we discussed pipelining, the bias-variance trade-off, cross-validation, and built our very first model baseline. In this section, we're going to cover how to tune our models, leveraging some of the techniques we learned about in the prior section, and ultimately how to select the best model for the job. We'll start this section by covering the concept of hyperparameters and how to define a hyperparameter search space in Scikit-Learn. Next, we'll cover a bit of theory around cross-validation in grid searches and how we can more ably control our splits. Finally, we'll pit several models against one another by tuning the optimal hyperparameters using grid searches and select the model that best performs against our test set. Here we are at the first video where we're going to discuss hyperparameters, what they are, and how we'll be using them in our next few videos. In this video, we'll first define hyperparameters before discussing how we can use them in various search techniques. Next, we'll analyze various methods for determining appropriate search spaces, and finally, we'll revisit pipelining and why naming conventions matter for hyperparameters. The term hyperparameter can be a bit terminologically confusing to someone from a computer science background who may understand parameters to be inputs to a function. In machine learning, hyperparameters are the metaparameters that control how the algorithm learns, where parameters are coefficients or decision functions learned by the model itself. If we go back to our high bias regression model we fit in the previous section, the theta vector, or coefficients learned, represent the model parameters, while any regularization terms such as lambda for an L2 regression model represent hyperparameters. Examples of hyperparameters with which you may be familiar may include the number of estimators for ensemble methods like random forest or gradient boosting, kernel type for SVM, or regularization penalties for various penalized regression models such as lasso or ridge. The example above shows the difference that can be made by tuning different hyperparameters. Selecting the appropriate kernel method in an SVM can make all the difference in the world. Notice the difference between a linear kernel in the above solution or a radial basis function in the bottom. Let's move into a quick example of how we define hyperparameters in Scikit-Learn. In this example, we're going to look at how to define hyperparameters. We won't end up fitting any grid searches, but we'll show how you can set up the hyperparameters for a grid search run. Scikit-Learn defines two types of grid search: the grid search CV, which is exhaustive, and the randomized search CV, which is randomized. Both of these are available in the Scikit-Learn model selection submodule, where you would find k-fold and other cross-validation types. A grid search is a strategy we can use to fit a model repeatedly over a search space of different combinations of hyperparameters in order for us to find the most optimal combination that maximizes performance against some scoring metric on a dataset. The two types of grid searches, exhaustive and randomized, have different trade-offs. Exhaustive searches will look over every combination of hyperparameters you provide. This scales combinatorially and can be very expensive. Randomized searches will randomly sample combinations of hyperparameters and are generally much faster. There is no hard and fast rule for which you should use, but it always comes back to your business requirements. You should always select the best model that can be fit within your time constraints. For this example, we're going to use the breast cancer dataset that is natively stored within Scikit-Learn. We can load this dataset from the scikit-learn.dataset submodule as we have Iris and Boston. As always, we're going to go ahead with our train test split and make sure we seed our random state. Notice right off that our training set only has 455 samples. This is going to come into play when we talk about different parameters that are realistic, or hyperparameters. Also notice that we only have 30 features. This could be many or few depending on how you look at it, and again will impact our search space. There are different ways to set up a hyperparameter or a grid search within Scikit-Learn. You can run a grid search without a pipeline, which is generally unrealistic since most datasets are going to require pre-processing techniques, but it can be done. We can define a hyperparameter search space with a simple dictionary, where the key is the name of the hyperparameter itself, and the value is some type of iterable in which different combinations of hyperparameters exist. If we use our random forest, with which we should be familiar at this point, we can search over a different space of number of estimators. We can define 10, 20, all the way up to infinity, different estimators here, but whether it's reasonable or not is a question for you to answer. If we use 10,000 different estimators on a dataset with only 455 different samples, the trade-off between the variance reduction in our model for greater number of estimators and the runtime is likely to be marginal and even not worth it. Therefore, we might select a smaller number of estimators. If we select up to 1,000 potentially for max depth, for a data set of 455, note that we're very likely going to overfit each individual tree, and a lot more trees will be required to reduce the variance in our model. For min sample split, this is the number of samples present in each split. If we have 500, we're going to have very high bias individual trees, since 500 is greater than the size of the training set. Therefore, we would only have one split. If we set up with a pipeline, it's a very similar setup, except notice that we have a different compound prefix in front of all of our keys. Our pipeline, as we mentioned before, takes a single argument, a list of tuples, length 2 tuples, where the first argument is the name of the stage and the second argument is the stage itself. As a simple example here, I'm using the select kbest feature selector. I've named each of these according to what they do, and the name is used to designate which stage the hyperparameter corresponds to. For the select kbest, we can search over the different k values we might want to use in our randomized search space. Notice here that I can define parameters within the estimators themselves inside of the pipeline, but this should only be used for non-variable hyperparameters. In other words, if I'm going to tune the number of estimators, I would not set that inside of the pipeline itself. Now, what we've shown so far would work either for exhaustive or randomized hyperparameter searches. However, for random searches, we can get a little bit more clever with how we search. Anything that's inside of an iterable here in a grid search is going to be susceptible to a uniform sampling with replacement. With a random search, we can get a little more clever, and we can either use a normal distribution, uniform, or even a random int, and we can pull in these functions from scipystats. Any sampling function is valid here. So if we use a list, then this is going to be uniformly sampled with replacement. If we use a randint, then we're going to be sampling from this random int space. We could simulate the same thing with a range, but we don't have to here. And we can even create this uniform distribution generator here with mean as the first argument and standard deviation as the second argument. Using scipystats generators here, we can create a more clever way of sampling from a randomized search space. Like I mentioned before, we're not going to fit in this notebook. We can just set up how we intelligently define the randomness of our parameter searches.